Before starting, I want to give a tribute to some of scientists which have been frequently at this conference and are no longer with us. This is first on the left side, Dieter Michel from Leipzig, who gave almost lectures on solid state NMR. I had the pleasure to perform with him in concerts where he played the organ. It's Kolya Sergeyev, one of the leaders of the Moscow University group in NMR, and Stefan Jurga from the university in Poznan, who used NMR, EPR, almost any analytical methods for investigations in physics, chemistry, and biology. Just one more picture. These are our friends in Kiev. Hopefully they are still alive. Also they left already their home country. Well, what I would like to say is that scientists share common interests and common values. And I hope that we all together in the near future will be together in a friendly and fruitful atmosphere. Okay, back to Richard Ernst. So I start with music before coming to NMR. So already in the age of 11, that is what Ernst writes, he played the violoncello and he loved to analyze music and to compose music. In the age of 12, he wrote his first compositions. He writes, "This helped me to overcome my low self-confidence. Today I believe that occupation in scores and classical musics was my entry to the secrets of chemistry. Isn't the chemistry comparable to a symphony? Like various instruments, art and its molecules must come together to create something new. And like a conductor, the chemist must completely understand the matter and their properties to create something new of a chaos. Today in my higher age," he writes, "my memory is no more the best, but the melody of a solo sonata of Bach and of the octet of Stravinsky forever sound in my mind." Interestingly, you can find similar thoughts in the marvelous book of Anatoly Leonidovich Buchatchenko, Chemia как Musica. I really recommend you to find it and to read it. So, Richard Ernst studied physical chemistry in the ETH Zurich. ETH means Eidgenössische Technische Hochschule, probably one of the best universities in Europe and maybe worldwide. And he obtained a degree as chemical engineer of the ETH. Already for his PhD thesis, NMR spectroscopy with stochastic high-frequency fields, under the supervision of Hans Primas and of his institute director, Hans-Heinrich Günthard, he received the silver medal in '61, which already is a good achievement in this university. But Richard Ernst writes further, "But Primas and myself soon came to a limit. We could not ever offer better spectra to chemists, and quantum physicists were not interested in our results as well. Finally, all my work seemed unnecessary to me, and I wanted to do something useful with my knowledge in NMR. Just at that time in California, the company Fourier Associates had brought the legendary H60 to the market, which began to establish NMR worldwide as an important chemical procedure. In October '63, I finally married Magdalena Kienholz and convinced her to join me to California. She became very important for my scientific work. She kept me free and understood my sometimes furious workaholics. Without complaints, she took over all duties of our household and the care of our children." It's important to mention the situation at Fourier at that time. Richard Ernst writes about that. At that time, Varian was a gathering pool of scientists and engineers from Stanford University, maintaining still close connections to the scientific community. My boss, Wesley Anderson, had made his PhD on NMR in the laboratory of Felix Bloch. I joined Wesley Anderson's work on optimization of NMR spectrometers. The recording of NMR spectrum with a frequency sweep or a field sweep was quite time-consuming. Therefore, we had another idea. If we irradiate all frequencies in a spectrum at the same time, all frequencies should respond simultaneously. In this case, the signal looks like noise, but an appropriate filter would allow to separate the useful from the useless information and to retrieve the spectral information. This filter, or better algorithm, is a mathematical equation of the Fourier transformation. With this algorithm, the measurement took only milliseconds, and Wesley and myself succeeded to produce a simple spectrum out of a chaotic signal trace which clearly showed the chemical information. But the signal evaluation was quite cumbersome. First, the measurement signals had to be transferred from punch card to magnetic tape. Then the Fourier transformation could be performed only in one of the early IBM computers, which belonged to the bookkeeping office. My colleagues mildly smiled at me when I made measurements in milliseconds and needed days or weeks for their evaluation. Anyway, finally, our results, after being rejected from the Journal of Chemical Physics, were published in the Review of Scientific Instruments. But the reaction of the scientific community was still controversial. Nobody could imagine that the technique would nevertheless be established. We can shortly follow the main steps of the discovery in the laboratory diaries of Richard Ernst. So he started actually from scratch. He defined the sampling for a simple cosine function. And this, of course, should apply as well for a sum of cosine functions with different frequencies, which normally represent the signal. Here you see, and he divided, he set data points of, in the case, it was 1024, 1 over m, the number of the data point. Then finally, he tried to calculate exactly what comes out of a digital evaluation. This is shown on the upside, and then the analog evaluation. For this, he even integrated the signal over all the sampling periods. And finally, he found unwanted attenuation at high frequencies, and he tried to remove this by shape shifts in the channels. So, and finally, he compared it with an experiment. So he writes further then. I had been very successful at Varian, but in '68, the situation at Varian has changed. The Varian brothers had died, and the new managers of Varian had no understanding of the potential of Fourier methods. Also, this could have been a real gold mine. Therefore, and additionally for family reasons, Ernst decided to go back to the ETH Zurich, where Heinrich Günther had offered him a job. So finally, it was not Varian, but the Swiss-German company Bruker, who, consequently developing a Fourier transform, developed a spectrometer based on this idea. Well, Varian had to develop high power amplifiers and pulse generators. Already at Stein time, this all was available at Bruker in serious production for their pulse spectrometers SXP 4-100 for measuring relaxation times in solids. So buying a fast signal averager from Fabritech and a computer PDB-8 from Digital Equipment with a program for Fourier transform, the Fourier spectrometer was ready, and it was on the market already in '69. And here you see on this slide, this is a really historic one. you see Tony Keller, later director of Bruker, running the first carbon-13 spectra, and this, of course, turned out to be a revolution for organic chemistry. And what you may see here, that is a normal Bruker spectrometer from that time, but here you see the signal average for Nicolette. Here you see the computer from digital equipment, and that's all. The spectrometer was ready. So, but there was another problem. Bruker wanted to get into the market of high resolution NMR. And there was one problem. And this problem was that Varian had all the patents for Fourier transform, and this prevented, of course, Bruker to enter this market. But in his opening lecture, Vladimir Žižek has mentioned the oral paper of Fyodor Ivanich Skripov. You have seen this slide already. I come back to it. Vladimir told that this work has been almost completely ignored, and it's not completely true. It's an interesting story. In '66, I myself, together with Barbara, was in St. Petersburg, and I bought a small booklet, Вестник Leningradskого университета, серия физическая, and there I found this paper, and I remember that paper. So just to repeat again, this was a measurement made in the Earth magnetic field of triple-tyl phosphate, and the signal you see here, and by hand calculations, Skripov transformed it into a spectrum. The spectrum is here, and it's since it is made in the Earth magnetic field, the chemical shifts almost disappear because they scale with the field. So what you see here are the couplings from the protons to the phosphorus, and in the center line, these are the protons which are far away from the phosphorus. So actually what you finally have here is a superposition of three triplets. That was at least the explanation. And now I told that to Professor Laupin in when we talked together, and he couldn't believe me. The next morning, I brought him this journal together with a translation into German made by myself. He immediately took this journal, and I never got it back. But it hopefully, it played a very important role in the lawsuit Bruker against Varian. And this lawsuit finally ended in a mutual license agreement that Bruker could use all the patents of Varian and vice versa. So this paper played a very important role in the scientific and as well in the commercial history of NMR. So here you just have the outline of the experiment. You all know that quite well. You need a pulse to excite the spin system, and there should be quite short pulses to cover a broad range. You get the free induction decay. For the sake of simplicity, there's only the chemical shift shown here, and then you get the spectrum. So what was the main achievement of pulse NMR, Fourier transform NMR? Of course, the enormous increase in sensitivity by a factor of maybe 1,000 or sometimes even more. Before that, NMR could be used for the most sensitive nuclei, proton, fluorine, and phosphorus. And now almost all elements in the periodical system which had a magnetic isotope could be measured with NMR. So what we can say is that Richard Ernst, with the help of Joseph Fourier, brought NMR to the complete table of Mendeleev. A connection to St. Petersburg, of course, in that case. So I told you already, Ernst went back to the ETH Zurich and he told that he was falling in the middle age. He writes, looking back, my return to the ETH in spring after the productive and inspiring years in California appeared to me like falling back into the middle age. My work was simply ignored. There was no interest in innovations. Nevertheless, in '69, I received the Ruzicka Prize for my comprehensive and deeply founded analysis of the problems of sensitivity in NOR. He struggled for recognition, and in '70, he suffered a complete nervous breakdown. He was 36 years old, and he was afraid that he would miss his scientific goals. He retreated to the home of a friend in Tessin, and at that time, he writes, I listened to the music of many contemporary composers, like Igor Stravinsky, Carl Amadeus Hartmann, Charles Ives, and the symphonies of Dmitri Shostakovich. This experience has convinced me that the scientists need several legs to stand on for being successful. I slowly recovered, and I am today still proud of that fact. But all problems of the ETH remained. I only could fight them more quietly. We come to the next point. In '71, I speak with the words of Richard Ernst. In '71, fortune gave me a new chance. One of my PhD students brought me an inestimable finding from a summer school of young scientists in Bashkapole in Yugoslavia. In a lecture which he never published, Jean Genet from Brussels proposed to excite the spin system with 2 pulses and to record the signal after the second pulse, after the interaction of the excited spins with each other. He believed that this should give more information on the state and position of the atoms in the molecule. I had understood the idea of 2D spectroscopy immediately, Ernst writes. It appeared to me as if I listened to music. The sounds from various instruments follow each other. They overlap in a crescendo and diminuendo, forte, piano, pianissimo. The spins react. They speed up or slow down with the second pulse. Some of them have a gloomy, some have a bright sound. Some of them can hardly be heard. My feeling of harmony and disharmony for wave-like appearing and decreasing sounds and frequencies helped me enormously to transfer myself into the world of NMR and to develop further the idea of Jean Genet. I discussed with my students if it wasn't unethical to publish our results before Genet published his idea, but he never published it. We later have been in permanent contact with Genet. We regularly informed him about our results, and he told me that he was always happy to receive news from Zurich. On this slide, you see Genet with the student of Richard Ernst. But now, the flight through the heights of NOR continues. In '76, we got together with my colleague Kurt Wüthrich funds for a common project, development and application of 2D NMR in biomolecules. This was really ideal because Wüthrich, as a molecular biologist, had the applications and Ernst had the methods for that. So this cooperation became very famous as the so-called Zurich group. But in the last year, the equilibrium necessary for a fruitful cooperation faded away. Wüthrich was a self-confident, performance-oriented scientist. He wanted to determine the agenda. Some people said I had built a Ferrari for him to win the race. I always remained the shy, introverted researcher who preferred to think on new ideas in a quiet atmosphere. In 1986, we ended our cooperation and we took both our own ways. Just on the right side, you see the structure of a prion responsible for Creutzfeldt-Jakob, or the so-called mad cow disease, which was determined by Wüthrich and Ernst. And here, this part turns out to be the reason. If you change the conformation, then the disease starts. But that's not all. The 2D spectroscopy, of course, immediately led Richard Ernst into the field of MR tomography. This here is the sequence for Fourier imaging, and it's quite easy now. And this is a basis for for all methods which are used now in MR tomography. You have an excitation. Well, this is slice excitation, and you record the signal in the presence of a gradient. This gives you the points on the x-axis. Then you repeat that with a gradient at the y-axis. This gives another phase, and that recording goes on. So finally, you get something of a K-space. K is written here, and by a two-dimensional Fourier transformation, you get those images here. That's just an example of a human head in various sections. You all know that. You can selectively look to vessels, and you can do a lot more. So this slide should have been at another place, but no problem. Anyway, so thank you, Barbara. Richard Ernst in 69 got an offer from Professor Günther Laukin, the boss of Bruker, and for a cooperation. And Ernst terminated his agreement with Varian and became a consultant of Bruker. And this, of course, was very important. And at the end of his book, Richard Ernst writes about his cooperation with Bruker. Not at last, I would like to thank all employees of Bruker Spectrobrand for long-lasting cooperation, namely Tony Keller and Günther Laukin, who that's a company with caution and visionary strategy. Okay, let's go on. So, in 25 years of hard work, Richard Ernst has revolutionized NMR. The introduction of Fourier transform had increased the sensitivity by a factor of 1000, had opened NMR for all magnetic nuclei in the Mendeleev table. Multidimensional NMR had increased the information content of the spectra by orders of magnitude. And furthermore, Fourier imaging had become the basis for all modern MRI methods. What could be the final recognition for all these achievements? Well, flying back to New York from a Bruker seminar in Moscow, Ernst got a phone call from Stockholm. He was awarded the Nobel Prize. That is just the situation in the plane when he got this message together with the stewardesses, which of course congratulated him. And this shows him on the way to the ceremony together with his wife on the left. This shows how the Swedish king handles the Nobel Prize to him. And then finally you see him back in his hotel, relaxing in the hotel. Ernst never was a friend of big ceremonies. But now he is writing about his Nobel Prize. For me, receiving the Nobel Prize was an unbelievable satisfaction. Many years, every day I had taken the train from Zurich, from Winterthur to Zurich, to be at 7 o'clock in my office. Then at 8 o'clock in the evening, back to supper at home, and 3 more hours to work at home. I almost never had holidays. I had achieved a lot, found good friends, brave and excellent students and cooperators. But most of the time I had suffered from envy and jealousy. I was delighted to receive the Nobel Prize, but at the same time I was painfully touched, because I was the only laureate. Normally the prize is divided between 3 or 2 scientists. And the main reason for this feeling was my colleague Wüthrich, who was also believed to be a candidate. He believed to have lost any chances because it seemed unlikely that in the near future another Nobel Prize would be awarded in this field. He really went furious, and he asked me in a letter never more to mention his results in my lectures. This ended in 2002, when nevertheless he himself got the prize. I immediately sent him a letter and wrote to my diary, "Now I feel free." Later he visited me in my laboratory and we had a very open discussion, and he apologized for his annoyance in 1991. The Nobel Prize was clearly the summit in my life. Nevertheless, I suffered from doubts. Today I still often think that I not have deserved it. And even once I had a dream that I got a phone call and I was told that it was an error and I had to give it back. So far, we have been talking on NMR, but of course, these methods can be used in other fields too. And what comes into your mind probably immediately is electron paramagnetic resonance, because so similar to NMR. The technique is more or less the same. The only difference is you excite the electron spins instead of the nuclear spins. And one of the pioneers in that field was Arthur Schweigger, working very closely together with Richard Ernst. They were very good friends and they worked together. But there are several problems which arise from the relaxation times. In EPR, the relaxation times are in nano and microseconds. That means 1000 times faster than in NMR. This needs fast ADCs and signal averages, which have not been available at that time, actually. You must have short microwave pulses. And to cover the spectrum, you need high microwave power. This leads to a very long dead time of the resonators. So you have to use resonators with a low Q, and this leads to a loss of sensitivity. Therefore, for most samples, EPR Fourier spectroscopy does not lead to a sensitivity gain. That is a complete difference to NMR. Here you just see the problem. This is a signal of toluene, and here that's formally in the dead time, a big part of the signal gets lost. And here you see the resonator Q. So you have to adapt the Q value of the resonator. If the relaxation time is 100 nanoseconds, you can use a resonator only with a Q of about 100, where in continuous wave EPR you have 4000 Q value. So still no gain in sensitivity. You lose the signal in the dead time, and you cannot use high Q resonators. But this is just an example. Here you have the APR spectrum, Fourier transform, and lower side the continuous wave. Okay, nevertheless, it led to a very fast development of pulse method in EPR. I just show you only one example. I will not go into details. This is electron-electron double resonance. And if you move these the pumping pulse, then you get you modulate the electron-electron dipolar interaction between two unpaired electrons in molecules, and this turned out to be a very good method adding information to the NMR spectra. You get modulation here, the modulation frequency, and by Fourier transform you get the frequency, and this of course is proportional to the third of the distance. Okay, but maybe even more important was the application of Fourier spectroscopy in mass spectroscopy. This method is called ion cyclotron resonance. And it's interesting that this mass spectroscopy is very, very similar to NMR. It's just you can even use an NMR spectrometer. You can add to them a measurement cell, and you can do these experiments. It's interesting to tell that at the first person in the Soviet Union at that time who did ion cyclotron resonance, like that, was Ende Lippmann. He just used his NMR spectrometer, and one of his students had built him ion cyclone cell. That's just shows you the idea. You can excite ions, and you can do this by any method. You shoot them into an electrostatic cell. The ions they rotate around the magnetic field, and they induce a mirror current in the plates, which is measured. So then anything is straightforward. It's the same detection as you have it in NMR. But what is important is you get an unbelievable resolution in mass spectroscopy. So a very, very good mass spectrometer might have a resolution of 30,000. Here you can get a resolution about 3 millions. The reason is very simple. The frequency is the unit, the physical unit, which can be measured with the highest accuracy. I just want to show you only one example. You can excite ions very softly, so you can get very big ions, and you bring it into the cell. Here you have the measurement of the metabolites of an anti-tumor drug, and you get the complete information out of a mass spectrometer with this tremendous resolution. Of course, quite better known, maybe to all of you, is the Fourier infrared spectroscopy. And this idea is in principle old because Michelson already had proposed his interferometer in 1907. He got the Nobel Prize for that. Well, you have a source, you got the light, goes through a beam splitter, is reflected, and goes to the detector. Another part does the same, but the mirror, one mirror can be scanned. And this simply gives an interferogram. If you have here the path difference, and if you integrate this, you get the spectrum out, like the same in any other Fourier methods. But there is one thing special for infrared spectroscopy, which is different from NMR. Of course, you get a very big advantage by the multiplex advantage. You measure all frequencies at one scan. But another point is that if you do, when you did in former times infrared spectroscopy. You use the grating, and for good resolution, you always have to use very small slits. You offset most of the light. In infrared, you just can completely use a light source, which gives an additional sensitivity. And I only want to show you one example. I always try to give examples which are important for all of us. So this here is very interesting. This is an observatory at the Jungfraujoch in the Swiss Alps at an altitude of about 4,000 meters. And there's an infrared spectrometer located. And the light source which is used for this instrument is the sun. And this instrument has a tremendous resolution. It has a scan width of 5 meters by the moving mirror and gets a resolution of 1/1000th of a wave number. And this is the solar tracker. You can see it here. And on the left, you see measurements which are made very, very long time ago. These are the first measurements which showed the accumulation of cooling agents in the atmosphere, because receiving the sunlight into the spectrometer, of course, this light has to pass the atmosphere and shows the absorption. So some of the substances have been banned. This is one of the very beginning of doing measurements with the atmosphere and try to look on the climate. Interferometers in infrared can be made very small, so they can be carried actually with you. This is an application in forensic science. I will not go into detail here, just. And we come to another point, that is investigation of art objects with infrared spectroscopy. Here you see a lady working on a Fourier Raman spectrometer with a microscope in the Metropolitan Museum in New York. And this brings us finally back to Richard Ernst. So what you here see is a so-called tanka. And this tanka, that is a roll painting from Tibet, is a very ancient art. And Richard Ernst got fascinated by this kind of art, and he made himself measurements on that. So you can determine the pigments by infrared spectroscopy and make dating of these arts. Just to tell you more about this, because this is one of the most interest of Richard Ernst. He writes that tankas, they are the Tibetan roll paintings. They are embedded in Buddhistic culture, which reached Tibet in the 6th and 7th century. In spring 68, Magdalena and I, on the way back from California, made a side trip to Tibet and discovered these paintings. My scientific background at that time was not very helpful for a deeper understanding. Later, we created one of the biggest private collections of tankas. Fascinated for this art, I started investigations in their origin. And in 67 and in 2007 and 2008, I should add that this was only after his retirement, I acquired a Raman microscope and mounted it on a mobile platform in order to make contact-free investigations in my home-based laboratory. This had been never done on those paintings and was really pioneering work. It made me a worldwide expert in this field. For me, it was important to give something back to the Tibetan art and culture. I wanted to contribute to the revival of this rich and historical important culture in recognition of its importance to me. I was always devoted to the exchange and balance between Eastern and Western ideas, like in the program Science Meets Dharma. Dharma in the Tibetan Buddhism means the all-comprising rules of Buddha, and the secret of this program should be the mutual benefit of modern science and traditional Buddhistic culture. I hope that our strictly rational science will profit from this exchange. Here just I show you the favorite tankas of the collection for Richard Ernst. The left one is a beloved, most beloved tanka of Richard Ernst, and the right is that tanka which his wife loved most. And here you see Richard Ernst, already in higher age, after retirement, mounting a tanka on his platform to investigate it in his home laboratory in the city of Winterthur. And of course, this Raman spectrometer was a Fourier Raman spectrometer. So back in his life, after retirement from NMR, he still worked with Fourier transformation, on that time in investigation of art objects. So Nobel Prize winners often become persons of public interest and often are asked to speak about general problems. Richard Ernst concentrated on many things, and I just will here read for you what he wrote about education. I cannot close my eyes in the front of the state of our earth. I feel sorrow and fear. I recognize the beauty of nature, the kindness of many people, and the depth of human relations, which make our life worthwhile. On the other side, I am frightened by the destruction of our environment and by human egoism. Many people, especially in the West, live in abundant wealth, and in other parts of the world, poverty and need is prevailing. Shouldn't human beings be obliged to remove this injustice? Who could better take this responsibility than the academic community? I understand education in an all-comprising sense. It should build a complete personality and character, and should not depend on religions and philosophies. Only such an education will create critical personalities, which are able to estimate our situation. Multidisciplinary education is a must for all people working in the frontiers of science. I am convinced that the scientists with experience in many fields will bring more intuition into his work. Therefore, for me, it was important to put my life on more than one leg. For me, these were art, especially the Tibetan paintings and classical musics. The art creates worlds which include the complete bandwidth of all human values, from the cold science over fancy dreams to overwhelming emotions, which cannot be expressed in words. For me, music played this role. And therefore, just I want to come back to a concert in 2015, the city of Winterthur, where Ernst has been born and stayed his whole life. He never moved to Zurich. They proposed a concert for him, and he should choose the program. Ernst decided that the program should be devoted to Johann Sebastian Bach and to composers with relation to him. So he started with Anton Webern, Richard Kare, 6, which he took from the musical offering of Johann Sebastian Bach. Then the third Brandenburg concerto, And interesting, this concerto has no slow second part. It's simply missing. There's only a cadenza. Therefore, as a missing part, he put in a composition, The Unanswered Question by Charles Ives. Then followed Igor Stravinsky's A Concert for Piano and Wind Instruments, because this was performed 80 years ago at the same place, conducted by the composer and with his son Sulima as a soloist. Finally, there was the last part of the Fourth Symphony of Brahms, because it's based on Johann Bach's choral, Nach dir, Herr, verlangt mir. Well, in English you would say, to you, God, I'm longing for. This concert was a big success, and Ernst was very happy to have expressed himself as through music. A last statement of Ernst. My life was a hard journey, full of emotional heights and depths. This might be true for any sensitive person, but I believe to be rather excessive in this respect. I often felt thrown down from one extreme to the other. And whenever I had arrived at the summit, I was frightened to fall into a deep, bottomless gorge. I do not remember how I appeared, and I probably will not recognize when I will be ready to go. My life is more or less a sleepwalking. Sometimes I awake, and I do not remember how and where I fell asleep. It's like a slow departure, not painful, not frightening, only in the wish to find my eternal rest. And this finally happened at the 4th of June last year. What Ernst has left to us? He had left NMR, Fourier and the Fourier transformation. He made NMR the universal method it is today. And he had a lot of co-workers and students. They are listed up here, and some of them are really great scientists. I mentioned them here and show you in yellow. Geoffrey Bodenhausen, he continued the work in 2D and multidimensional spectroscopy, creating very nice sequences and pulses. Griesinger continued the work with NMR in biomolecules. Gunnar Jeschke is, for my opinion, for the moment, the leader in pulse EPR. Malcolm Levitt created ingenious pulse sequences. Maudsley was very important for MR tomography. Beat Meyer is the man who succeeded the chair of Richard Ernst. Nagayama was, together with Wüthrich, one of the pioneers for NMR in proteins. Arthur Schweiger was the initiator, actually, and one of the most important persons for pulsed EPR. Nikolai Sklinikov has given several lectures here at the conference. He was a student and visited Richard Ernst as well. The same for Ole Sørensen and many others. Just again, some pictures of Richard Ernst from his short visit to the Soviet Union. You know, I think this person here, that is Barbara and Aganov. This was at a conference in Kazan. You see here the late Kolya Sergeyev, and with him on at his left, Griesinger and Gurevich and myself. So finally, I only can express my very, very deep appreciation to the extraordinary scientists and to a fascinating personality of Richard Ernst. He did everything that he could not, and in his biography, I think he wrote probably because he didn't want to appear completely behind his fascinating work. So, and I really would encourage you to get this book and to read it. Thank you very much for your attention.
Okay. Okay, thank you very much, Uwe Eichhoff. Unfortunately, your time is over, but we could give you one, two questions. Yes or no?
Of course, I'm ready to answer a question. No problem.
Dear Uwe, this lecture is very remarkable. Close to Richard Ernst worked another Nobel Prize winner, Kurt Wüthrich. Do you know anything about his life?
Well,
last time, Kurt Wüthrich visited 15 years ago our center, and we have had good conversation with him.
Well, Kurt Wüthrich as well was a consultant for Bruegel, so I met him several times as well. He is younger than Richard Ernst. I think he's retired, but probably still active. Well, that's the only thing I can tell you for the moment about Kurt Wüthrich. Actually, it's really, if you took them both together, they are very, very different persons. So this is really, and that's understanding that. Okay, yes.
Okay, then thank you.